Yeah, so we'll see. Yeah, so my idea was I wanted to go through some things that Krishna didn't have a chance to cover, or maybe wasn't planning on covering, but I think is kind of useful to just start thinking about simplicial sets as not just being nice geometric objects, but also a nice category of things to work in. And then we'll build up some examples and whatnot that might be useful later. And then we'll go on to Dold Kan and do some of that. So what I wanted to first do is, well, so we've already seen some constructions of simplicial sets. So, for example, we saw that there's products, co-products, and mapping spaces. And so what I want to do first is just to describe some more general constructions that we can apply to uh, produce more interesting simplicial sets. And a lot of this is motivated by the following easy to prove lemma, which is that the category of simplicial sets has all small limits and co-limits. And the proof of this, I mean, I won't go into a ton of detail, but it's really just the fact that set, the category of all uh, small sets, has all uh, small limits and co-limits. And it's a general fact and category that if you have functors from any category to one that is has limits and co-limits, and that too will also have all limits and co-limits. So this is really just from the definition of what we started with. Um, and part of this lemma is actually something a little more, which is that these limits and co-limits are really easy to compute. I mean, computing limits and co-limits in set is very manageable, and we can compute these all point-wise. We can do this just purely by working on this side of things. So that makes our life pretty easy. And anyway, there's lots of constructions that you might know from various versions of topology or algebraic geometry that can then be applied here. And so let's see some examples, starting with some old ones. So the first one is products and co-products. So we didn't actually give a rigorous definition of these last time, I think, but uh, now we can. So if X and Y are simplicial sets, then the product is, well, is simply a limit. This is a very general thing. Um, and the coproduct is a similar colimit. So this isn't anything really new. This is just rephrasing it. And this allows you to actually write down things like the face and degeneracy maps explicitly just by using the fact that they're realized as limits and colimits. So the next one is related, and these are sort of like relative coproducts, or the way I like to think of it is just gluing. So if we have three simplicial sets along with some morphisms z into x and z into y, we can then define the coproduct over z as the colimit. And the way to think about this topologically is that we have some space x, some space y. They have some intersection we're gluing together to get, I mean, there's some part Z that we're gluing along to get a bigger set, and this entire space is this relative coproduct. So we can glue simplicial sets out of old ones. We can also take quotients, which I'll add this here. So if we want, we can define the quotient of x by z as the co-limit z to x. And now we just map everything to the terminal object point. And so again, what we should think topologically is that we have some set x, we have some piece inside z, and we're contracting that to a point. We're forcing it to be identified. And so I don't know how to draw this other than just, I don't know, calling this x mod z, something like that. So we saw this last time as well, where we were constructing this simplicial, this minimal simplicial circle, and the way we constructed that is by a quotient. And again, we can go and think about this purely categorically. Okay, any questions so far?
Not a question, but a comment for those who are seeing this for the first time. You can think of co-limit just as a fancy union and limit as a fancy product. You know what a product is, right? And you know what a union is, right? Just think of their fancy version in terms of co-limits and limits. That's all.
Yeah, I mean, I think there's a lot of nuanced behavior in this, and I think we'll see a lot of souped up versions of this in the future. But I think more than anything, it's a way of writing things precisely but quickly. And if, I mean, most of the ideas that you have constructing topological spaces from other ones probably can be written in some way as a limit or a co-limit in some way.
Exactly.
So,
Yes. Yes.
uh, anyway, uh, so the next one that I wanted to do was a sort of related one, which is I don't know. I mostly just wanted to include this because when you learn algebraic topology, this is like the foundational construction that you encounter, and that's this idea of like mapping cylinders or cones. And let me so let's take a morphism from x to y of simplicial sets. And then we can define the mapping cylinder also via a colimit. So we take a copy of X, and there's a natural map to Y that delta zero is just a point, so it's not really playing any role here. And then we have a map to delta one, and it doesn't really matter which one you pick, but I'm going to pick the one that takes 0 to 0. Cross with the identity. And so this, you take this colimit and you produce, I mean, some simplicial set. But the idea that you should have in your mind is that we're gluing the 0th piece together with a copy of Y along this map F. So you've seen this in topology. We have this cylinder, which is this delta 1x. And on the top, we have some 0 cross x. And on the bottom, we have some 1 cross x. And we're not doing anything to the 1. But what we're doing is we're gluing together with a copy of y. And we're quotienting out by this relation that 0 comma x should be identified with f of x. So another, nice construction, although I'll say I think it's a lot less interesting for simplicial sets just because the possible maps between simplicial sets is a lot more constrained than topological spaces, but this is also a good thing. And so we can do a similar process, but instead of where we work with a cone rather than a cylinder. So this is this mapping cone. And you can describe it in a few different ways. I have this sort of, I don't know, I think it's kind of fun to describe this using the mapping cone. And so what we're doing is we want to crush the we want to crush the top to just a point. So we have uh, delta 0 x, and then we're going into delta 1 of x, and there's a natural map, or I mean, a universal map that goes into the mapping cylinder. And I think I want this to be D1 now.
Uh-huh.
And we can go down to delta 0. And so this is just obtained from the mapping cone by crushing everything on the bottom. So we have something like this. And it's quotient out by the same relation. So the top is 0 cross x. But now we have it all the way contracted to a point. So these are useful. It's I think we'll start seeing these more when we talk about the homotopy theory of these simplicial sets. They play a very analogous role to those that you would construct in algebraic topology. Okay. Um, Now are we ready to do something more I don't know, unique to simplicial sets? Okay.
Yeah, it's
Yeah,
just that
okay.
I
Good,
will
good, good.
just make one comment here.
Uh-huh.
Note that for any map in topological space can be factored through this mapping cylinder objects, such that x2 mapping cylinder, it's a cofibration, a fancy injection, followed by a homotopy equivalence. That MF thingy in topological spaces is equivalent to your y. And last time we talked about your homotopy theory of simplicial set is that simplicial sets that are built upon mimicking the homotopy theory of topological spaces. So by that, you should already be guessing in the back of your mind this MF thingy can be similarly replaced by that y object homotopically. So that's just one remark I would like to make. That's all.
Yeah, yeah. I mean, we can I don't want to spend too much time on it, but like it's very useful to describe like to be able to just talk about a mapping, for instance, like null homotopic via its mapping cone or something acid that's contractible, and you can do the same thing here. This is a useful idea, and in some sense, this is the correct idea when you work with simplicial sets. Like maps should then like everything should be regarded in some simplicial way so that you can really just talk about the underlying simplicial set being contractible or having certain homotopy groups or whatever, and that's good enough. Okay,
Mhm.
so I think the last thing I wanted to touch on was or hopefully last, I haven't scrolled on my notes far enough, but is this idea of skeletons. And this is something that is quite unique to the story of well, simplicial sets, but I mean, there's also versions of this for CW complexes or simplicial complexes or whatever. But the idea is that, when we think about like, why are simplicial sets so nice to work with? Well, part of it is that we can go and look at just the zero dimensional things, the stuff built from zero simplices, and then add on the one simplices and add on the two simplices and so on. And this process may take forever to complete, but it's a worthwhile endeavor. And it lets us do these inductive arguments where we can just figure out things at different stages. And so I wanted to make this precise and like, how do we actually make sense of this notion of like a skeleton? And yeah, anyway, so let's get into it. Um, and so I'm going to give two different definitions. One that is nice and easy to write down, but is perhaps isn't categorical like the ones that we've seen previously, and then we'll give a categorical definition as well. So maybe we start by just fixing some simplicial set and taking some integer that's greater than or equal to 0. So the first definition is that the k-skeleton of X well, this is going to also be a simplicial set. So I'm going to write down what its n simplices are. And it consists of the n simplices of x such that they factor all the, sorry, how do I want to say this? Well, let me write down and then I can figure out what I'm trying to say. Um, so for all the m that are below or the same as k, we can factor the map sigma. I mean, sigma is a map from the n simplex into x. I'm viewing x as being some ambient set, and this is a little hand wavy, but that's okay. And it should factor through delta m. So it's this thing that the we're discarding anything that plays a higher role in this uh, simplicial set. And I mean, the intuitive description,
K. K is the kth skeleton of the
it
simpleton set.
yeah, this is the kth skeleton
Okay.
of X. So
So
I mean, the intuition here is that the kth skeleton is obtained from X by throwing away all the higher simplices. The k plus one, or I guess the uh, greater than k simplices. And so one has to be careful about this because I mean, when you talk about like simplicial complexes, there's only finitely many simplices, and you stop, and it's like, okay, we're done. When you're talking about simplicial sets, you usually have many, many, many degenerate higher simplices, and so this thing still has higher simplices. It just doesn't have like non-degenerate ones, and so there's some care you need to do. But I mean, this is uh, yeah. So what this condition that I mean what this is doing is it's saying we're only taking the simplices which are degenerate for sorry, that are non-degenerate when n is less than k or less than or equal to k. So let me write maybe a more satisfactory answer to for some people, and this is I think quite nice. And so let's look um, at so we have our standard and some standard and simple sorry our standard simplex category, and we can look at the I don't know what to call this n truncated version of it. So this is a full subcategory um, whose objects are just the integers that are below n. So they're m with m less than or equal to n. So it's not any harder. We're just removing everything higher. That's all. And what we can then do is talk about sort of this truncated version of simplicial sets. And I don't know what the notes use. I'm probably going to use non-standard notation or something, but I'm just going to call it S set n. And it's defined in the same way as we just take functors from delta n up to uh, set. This is perfectly fine. And what we can immediately notice is that, well, we have an sort of obvious functor from this truncated simplex category into the full one, and this induces a functor just by composition uh, from simplicial sets to this n truncated category. And I'm going to
No,
denote this functor. Oh,
this
sorry.
is not quite correct because you also have co-skeleton. Like this one is the right adjoint, co-skeleton is the left adjoint of the restriction. So they are different.
Uh,
I know what you mean by induced, but this one is the right adjoint.
uh, yes. Okay. Yeah, you're right. Sorry. Uh, yes, yes. So, yeah, the Yes. Yeah. So this I guess the point that I'm making is that I'm lying here, not so what we certainly have a functor uh taking you from uh uh delta op to delta n op, and this you can compose with set to produce a functor going in this direction. But this also admits it admits adjoints. Maybe not at this level.
Both the left and the right. Both the
Yeah,
left and the right.
yeah. So it admits a left adjoint, and this will produce. So let me. So the left adjoint.
Oh, a little bit. I'm sorry. So when I was, that's my bad. That's my bad. So when I say the adjoint, the left and the right adjoint, that's what I'm talking about is against the from of the restriction
Over here.
of the restriction. Yeah, of that one. Yes, yes, of
Yeah,
course. I'm sorry.
gotcha. Yeah. So this is like an inclusion functor right now. And we can it has a left adjoint. So maybe I'll call this I guess in star or something, and it emits a left adjoint in shriek, but it also emits a right adjoint in star. And there's sort of two notions that one can associate. There's the end skeleton of X, and this is with the left adjoint, I think.
Co-adjoint, co-skeleton should be left, I guess.
Okay.
I'm not very sure. Sorry about it.
So maybe we'll put a question mark
Yeah,
for which one it
yeah,
is.
yeah.
It's a subtle thing. Anyway, and so the other one should be whatever. I mean, the co-skeleton is whatever the other one is.
For others,
Prior.
there is a very similar thing, analog of this, like the co-induction and the induction. It is
Yeah.
exact same thing. I should say, because one is the restriction; it admits both the left and the right adjoint, and one is called induction, the other one is called co-induction.
Yeah. So I mean even closer. I mean so simplicial sets are pre-sheaves. And you have a restriction functor for pre-sheaves. And I mean it has sorry, you have a direct inclusion for pre-sheaves on like closed sets, and it emits a left adjoint and a right adjoint. And I mean this is this same idea where you're like, how do you produce the like I mean yeah, this is the restriction followed by like a proper push forward of sheaves or something. Maybe like with some caveats. But yeah, I mean so I won't say too much more about this other than like I mean I said these adjoints exist. I think that's kind of a loaded thing. So the way that they're constructed, so both these are constructed via con extension. So there's a sort of general way of constructing adjoints, and the methodology for I mean the reason one can do this is really just because of this fact that we have all these small limits and co-limits, and this functor we wrote down here plays nice with respect to them. So we're able to go in and force these into existence. And so I don't think it helps too much to write down explicitly what it is, but if you've seen any of these sort of con extension constructions before, it's pretty easy to guess. And
Can you say more on the functor from opposite? So you have an inclusion functor from delta n to n. So what is the functor from delta up to delta n up?
are you asking what this functor is?
Yeah. So what sends object to?
Yeah, so I think maybe do I have something
No, you have already written it. It's quite clear. So you have delta n included into delta. So you have delta op to delta n op.
Oh, opposite didn't change
no,
the
I think no, I think
Oh yeah, quite right. I'm sorry. Yeah.
yeah, so I think it is supposed to be this. And okay, this makes
Restriction
things
is the other way. Yeah, restriction is the
yeah.
otherwise it's
Okay.
not
Yes.
called restriction.
Yes. Okay. Yeah, this I want left adjoint.
Wait.
Sorry, okay, give me one.
Yeah, that's correct.
Okay, so I think I want this to be called this. The left adjoint should be upper star. This one should be like upper shriek. And then I think everything else is the same. Yeah, is this oh sorry, these should be flipped, but okay. Are we happier now?
Sounds great to me.
Okay. Yeah, sorry, this makes more sense too. I mean what you're fundamentally doing is oh wait. Anyway, yeah. Or maybe I still have things. Okay, I think we want this to be the restriction. We want this to be the left edge. Okay, there we go. Sorry. So you restrict should be like it should be a pullback. It admits the left edge joint and a right edge joint. And then what we're doing is we're taking X, we're restricting it to the end skeleton, and then we're sort of freely pushing it. We're pushing it forward in some way. And that's what produces this end skeleton, and vice versa the co-skeleton. And but before we go on and see a couple of sort of sub-examples of this, I want to make this sort of remark, which is that like every simplicial set can be constructed from its skeletons. So it's not hard to prove just from this sort of general formalism, is that if we take the co-limit over all n greater than 0, then X is the co-limit of its end skeleton. And I mean, the way to interpret this is we're taking a union of all the end skeleton, so you get the whole thing. And the like really the only thing that's worth noting in terms of like how you prove is this fact that if we first push forward in either the shriek or star sense, and then we pull back, we just get the identity on simplicial sets, truncated simplicial sets. And so you have to sort of like apply this iteratively or something, but it's not too bad. Okay. Any other questions before we see a couple of examples? Okay, so let's write some examples. So I think the most like primordial examples we should look at are just like, what about an ordinary simplex? So if we look at, say, the two simplex, well, the way we want to think of this two simplex, I'll draw all the non-degenerate faces of it. And so it consists of 3 zero simplices, 3 one simplices, and one sort of, well, I should sorry, 3 zero faces, three one-faces and one two-face, and the skeleton is exactly how I described before. So it's the zero skeleton is just going to be these points. So it's just a disjoint union of three zero simplices. And the one skeleton is everything except the two face. So it looks like 0, 1, 2. And then when we take the two simplex, we get back to where we started. Or sorry, the two skeleton, we get back to where we started. Likewise, for all the higher ones. And so like, I mean, this is, I guess motivates also partly this like definition, which is if we want to talk about the boundary of an n simplex, all this is the n minus one skeleton. So it's what we get by throwing away that n face. And so we can actually from this also define things like at least some model of an n sphere. And this is just given by taking our n simplex and then modding out by its boundary. And using this quotient description we gave before. So I think maybe Krishna gave another definition in terms of suspensions, but you can also do it this way. Another sort of related example is this idea of a horn, which I think we'll need in just a little, well, not today, but in the future. So if we look at the boundary of our n simplex, we can, this is just the n minus one skeleton. And what we saw in this example is that there's sort of a very nice description of this. This is just a union of, in this case, three one simplices. And so what more generally happens is that if we look at the boundary and we remove the n minus two skeleton, then what we get is, and I'm being a little haphazard about this, but I think this is morally correct, is that we get a union of n plus one n minus one simplices. And so we could then define the kth horn of the n simplex to be this boundary where we remove the kth copy in this union. This is the kth n minus one face of say delta n. Sorry, the kth, yeah. So to make this more clear, we have our 0, 1, 2. This is the boundary of the two simplex. And so then we have three different horns we can define. I should do this in the correct order. And so we're removing the face opposite of that vertex in this case. So this is the 2, 0 horn. This is the 2, 1 horn. And this is the 2, 2 horn. So hopefully I got all those correct. But yeah, I guess a very key component of doing like homotopy theory for simplicial sets is these sort of like lifting problems where you want to take a map from a simplicial set or particularly like an n simplex or the boundary of n simplex or the horn of an n simplex and ask when you can extend it in some meaningful way. And this will get into a lot of model theoretic business we'll see later. Okay. Any questions before we go on to Dold Kan? Okay. So the goal is to talk about this idea called the Dold Kan correspondence, and I mean, there's lots of different interpretations and various degrees of generality, and we'll focus on the easiest one, and then maybe make some remarks on some of the more general ones. But the basic idea is that, well, and like right right now, like we've seen one example of what's called a simplicial object or category of simplicial objects of some category, namely simplicial sets. These are the simplicial objects in the category of sets, which is a little bit of a tautology, but not entirely. And we can do the same thing with other categories, and sometimes they have nice descriptions, and sometimes they don't. But the one for abelian groups is quite nice, and it gives us some insight into the like how we think about cohomology of like topological spaces. So let me start with some notation. We have the AB for the category of abelian groups. I'm not assuming any sort of like finite generation or finiteness of these because I want these to be like complete and co-complete. And then we can define the simplicial abelian groups. And this is just the simplicial objects in the category of abelian groups, i.e. the maps from the simplex category, or the functor category from the simplex category into abelian groups. This is called the category of simplicial abelian groups. I think in general, we might see a few of these today where you talk about simplicial so-and-sos, so simplicial sets, simplicial abelian groups, simplicial pointed sets. In all of these cases, the definition is very like, I don't know, stupid. It's the simplicial objects in that category that you're trying to define them in. Anyway. So with that in mind, like let's try to like break down what this data is actually entailing. It. What does a functor from this like what does one of these functors look like? So what this data should mean is let's take such an object. Well, we should be able to plug in just an integer and a positive integer and get something. So we should have a collection of abelian groups like an for all positive integers. And there should be some compatibilities with these given by the generating morphisms in the simplex category. So in particular, we should have more for our degeneracy maps to n, we should get corresponding maps going the other way of abelian groups. And we likewise, I mean, we have for the face maps, we have something similar, although I don't have too much use for these right now. So we'll have some SIs that go from an-1 to an. You take these for what they are. And yeah, I mean, this is fine. I don't know. There's not too much interesting happening here. There's lots of sort of trivial things we can do to come up with these things. So, for instance, if we have any abelian group, we can always define the simplicial abelian group A dot by saying that A0 is A and AN is 0 for all n greater than 0. And likewise, all the face and degeneracy maps will be 0. And I don't know, maybe there's other interesting examples people are aware of.
Is this really possible? Because you have to have identity. One of the identities going upward, then going downward should be identity. So all
Going,
the things, so what I know what you want to say. You should have like all the things are equal to A and all the
uh,
maps are identities.
yeah, thank you. Yeah, you're right. Yeah. So AN is equal to A, and then these maps are just identity maps on A. Yeah, you're right. Yeah, when we go up and then down, we should be came back to where we started. Okay. And so I don't know, there's something inherently leading about writing D lower I from A sub n to A n minus one whenever you're talking about like, I don't know, mathematics, and that it starts screaming that there should be some sort of like differential here. And indeed, like, you know, one way of thinking about this is that we have what we're like, I mean, yeah, and another example of like this sort of idea is that we can like think about the wait, this one example, and two is if we have a if we just have a simplicial set, we can think about the collection of we can think about this map from what do I say, from here, sorry, 2 billion groups, which sends oh sorry, okay, that sends n and maps it to all like this sort of freely generated by the n simplices. And then what these DIs and SIs, or what these DI correspond to in this case is these are these face maps one encounters in simplicial homology. So when you're defining this, when you define simplicial homology, you build up this chain complex, and you have a lot of different maps that you can take to take a an n simplex to n minus one simplex, and so you kind of do this averaging process to get the correct differential. And indeed, like, I mean, this can be done here as well, but this is sort of the prototype. It's before we've done the averaging. And so we can do the averaging then, and we can actually define this sort of process in complete generality. And so what we're going to do is define this map, I don't know, partial or del, oh, sorry, from AN to AN minus one. Here I'm just taking A to be a simplicial abelian group. And we're going to define this by should be this alternating sum that one encounters in your intro to topology classes. And as a map, this just goes from AN to AN minus one. And what one can check using the exact same argument that you do in intro to topology is that the square of this map is zero. And so, I mean, some care needs to be done in interpreting this, but I mean, if you start at AN, you go to AN minus one, and then you go to AN minus two, via the partial, that this composition is zero. And yeah, I mean, I wrote this as an exercise. It's a good exercise if you haven't worked at all with these face and degeneracy maps before, and because it lets you work with these simplicial relations or simplicial identities. But it really is just the same argument that you give when you're taking intro to topology and you're trying to show that this complex of that you build up is actually like a chain complex. And
I
so
always
what's
have,
the
can I ask a quick question?
Mhm.
Yeah, I always have this question that you have two set of maps, the DIs and SIs. You use DI to form a differential. So what SIs will help you to gain information on the complex? like additional you don't use for the complex?
Yeah, I mean, I guess there's some sense in which it tells you. I mean, what we'll get into with Dold Kan is it the co-simplicial maps, or sorry, the maps going the other direction don't tell you anything, right? Like it's not something that at least with chain complexes, it doesn't tell you anything. I think there is like this idea that uh, there's like chain co-complexes, which are not the same as co-chain complexes, and
Mhm.
this gets you can like dualize certain identities, and this is supposed to be like both a chain complex and a chain co-complex, and so there's a sort of like I think a contravariant version of Dold Kan that can be framed in this way, but think this is not as fashionable. I don't know a reason for it though. I think it partly is just because, you know, as mathematicians, we tend to care a lot about chain complexes. I don't know. If anyone has a better answer.
I
Um,
did more on chain complex because we are talking, I'm interested in Harshal cohomologies.
so
Ah,
Co-chain.
yeah,
actually, in the Hochschild cohomology case, the degeneracy maps are useful. So, for instance, take the bar resolution. How do you know that the bar is a resolution? It is because you can construct a homotopy between bar and the trivial one, and the homotopy does come from the degeneracy of the bar.
Oh, I see.
So in that case, it's helpful. And so this construction does not only hold for simplicial object. There is something called semi-simplicial object, and you can construct this as well. It's like you could there are some more general thing, but simplicial is better, and you should like it carries more information. It carries some information, yes. So even in the complex case, and we would say no, it's not very degenerate.
yeah. I mean, I think partly is also because we're like one aspect of this is we're working with like abelian groups, which is quite nice. If you change the category that you're working in, this quickly becomes. I mean, there's versions of Dold Kan that I think use a lot more. Well, yeah. I mean, I think for instance, if you want to discuss things like uh commutative differentially graded algebras versus simplicial algebras, and like simplicial algebras are the same via some Dold Kan to CDGAs in characteristic zero, but in positive characteristic they are not, and they're the sort of like degeneracy maps play a much more significant role in trying to understand this role of the differential when differential squared is zero being less meaningful. But I don't have anything too precise to say.
Okay, and thank you. Yeah, thank you for
Yeah.
that.
Okay. So yeah, I mean, what's the takeaway from all this? I guess the upshot is that we have this process now that takes something in simplicial abelian groups and it produces this chain complex, which I'm going to denote. Well, I mean, it's the same object. Just now we have this differential map, but this is a chain complex, and to be more precise, it's a chain complex concentrated in positive degrees or non-negative degrees, I should say. And so I mean, we're not going to go into all the details, but this actually defines a functor from simplicial abelian groups into these chain complexes, and I'm going to denote this sort of in a leading way by C lower dot, even though it's really not doing anything at a underlying set level, but it's useful to think of this as like how you define chains for simplicial homology. And this functor is I guess classically called the more complex functor. Okay. So what's nice about this? Like, why is this something we're looking at? Well, here's a really quick sort of application of this is now we have the tools to define what simplicial homology is. So we can define simplicial homology using this description I gave before, where we can take a simplicial set and produce a simplicial abelian group by looking at sort of this free abelian group on the simplices. I'm calling this Z adjoint X. And explicitly, these are just the polynomials. I mean, the n term of this is the polynomials in the n simplex, or sorry, the n simplices. And so we can define simplicial homology by just declaring that the homology of the homology of X is the homology of this associated chain complex. And the sort of fact, which we certainly will not prove, but is actually quite easy just from going through the definitions, is that if we take the, say, singular chains, or sorry, the singular simplicialization of X, then this actually just produces like simplicial homology or singular homology, provided that X is nice. So this is actually like recovering some topological information from this, just purely combinatorial. And it shouldn't be a surprise or anything. This is just kind of this process. So what is yeah, I mean, when you're, I don't know, when I first learned about Dold Kan, I kind of assumed that this would be the functor that like gives you an equivalence, like the like what we want is for this functor from simplicial abelian groups to chain complexes to be an equivalence of categories. But like this is not true. And the sort of problem is that we have these degenerate simplices. So we have a lot of degenerate simplices. Just, I mean, in general, but like, yeah, in some given one. And so like when we for example, like in this case that we saw before, with viewing an abelian group as an object in simplicial abelian groups, almost everything except the zeroth simplices is degenerate, right? It all arises via a degeneracy map from the one before it. And so what happens is, like, morally, we want is this abelian group to get mapped, like A should get mapped to just A viewed as a chain complex in degree 0. But instead we get something that's, I mean, so this is what we would like, but what we get currently, like what does C dot do? Well, it takes us to this chain complex where all the maps are 0. And so on. And so it's not right now we're getting too much information. We're getting too many things, and there's going to be some overlaps, and it's not tightly controlled enough. Like the number of maps, the endomorphisms of this as a chain complex is way bigger than the endomorphisms of A as an abelian group, for example. And so we want to go and constrain this and get rid of these degenerate simplices, so we can just sort of throw them away and this will get us what we want. So we're going to define the normalized chain complex. And we just need to specify what the simplices are. And it's just going to be the intersection of all these kernels. Of the sort of base maps, AI to AI minus one. And so if all these maps are identities, like we saw in this above example, some face maps there were all identities, then the kernels will be zero for everything except n equals zero. So we get what we want, at least for A being the sort of constant simplicial abelian group. And just as before, I mean the differential restriction, there's like certainly things to check, but the upshot is that we get a functor now from simplicial abelian groups to positively graded chain complexes. And at the very least, we know that if we plug in just a normal abelian group, what we get is A back, just viewed as a chain complex in degree zero. So this should be like hopeful. So I mean, this is if A is just an abelian group. And this indeed is and ends up being what we want. So here's the theorem of Dold Kan, which is that this functor is an equivalence of categories. This is quite nice. And I don't know, we have about 15 minutes left. So I don't know. I think this is like a really nice result. And it's one that it's like very unclear like what the use is from like just first glance. And it's also something where like actually proving it is I don't know, kind of miserable. Sorry, let me say one more thing about this equivalence. So I'll also say that it sort of has some like homotopy theoretic properties. I mean, it sends it sends simplicial homotopies to chain homotopies. So it's a little nicer than just being some abstract equivalence. So the actual, yeah, I mean, proving it is the most of the substance of proving it is actually constructing the inverse functor. And I have very little intuition for this functor and like really like where this is coming from in any meaningful way. It ends up being a lot of combinatorics and a lot of I don't know. Yeah, I mean, it could be its own talk for sure. Just trying to go into this, but it's also, I don't think, the most useful thing. Like having the inverse functor is not as meaningful as just having the functor from simplicial abelian groups to chain complexes in the first place. And I mean, I guess there's some use, but yeah. Yeah, so I think it's more useful to see like some like you know why should we care about this theorem and yeah, so here's sort of an application. So I already wrote down like one functor that takes Give myself a little more room. So we wrote down a functor before that takes you from simplicial sets to simplicial abelian groups. And it's sort of this like free, yeah, I mean, it's a free abelian group functor. I mean, it takes a set to its free abelian group on that set. And that's really all this is, just simplicialized or whatever. And it has an adjoint going the other way, which is just a forgetful functor. It just takes a simplicial set, sorry, a simplicial abelian group and forgets the abelian group structure. And so we can now just start computing with this Dold Kan. So let's take a simplicial set and take an abelian group. And let's look at the end cohomology of X with coefficients in A. So this is the same as if we were to look at these normalized chains in X with coefficients in A, where I shift by n. So this is all in the chain complex category. And what Dold Kan says then, well, sorry, I mean, yeah, so what Dold Kan says is that this is equivalent to classes of chain homotopies, or sorry, classes of simplicial homotopies to, I mean, here what I'm writing is gamma is the inverse functor of the normalized chain complex functor. So we can apply Dold Kan, and now this is in the simplicial category of simplicial abelian groups. And just right carefully, this is Dold Kan. And now we can use the adjunction that we wrote down up here to get that this is maps from X into the underlying set of this. So I mean, I think this is like some just notational shifting or whatever, or purely like categorical. But like, what is this really saying is that the Hn of X of A is homotopy classes of maps from X to this simplicial set here. And this is just an ordinary simplicial set now. And I mean, it's not a very complicated one either, but it's some ordinary simplicial set. And what we recognize from like intro to topology or what have you is that this is exactly how we describe the Eilenberg-MacLane space. So this is some model for the Eilenberg-MacLane space of A. So I mean, I think that alone is neat. We have a construction that's simplicial. That's, I mean, it requires some machinery, but it is what it is. But I think moreover, like this gives you some insight to like this is a not just any construction that's like a functorial one, right? So for instance, if we have a map A to B of abelian groups, then because all these things are functors, we get a map of Eilenberg-MacLane spaces. And then this description from above becomes sort of this base change map in cohomology. And likewise, we can describe, pulling back along cohomology classes in a similar way. So it really gives a way of getting some more insight into like just ordinary cohomology of topological spaces in some meaningful way. And I think that alone is quite nice. But yeah, I mean, so I think there's lots of like slogans for like how you think about these Dold Kan correspondences. I mean, they're some way of transferring information from homological algebra to topology in a meaningful way. And maybe I'll just also give a quick remark that abelian groups is not very special. And variations exist for well, are other abelian categories. And this is a very straightforward one. Somewhat more surprising is it holds for other additive categories. So things like triangulated categories as well. And also other stable infinity categories. So it's kind of like an increasing sequence of generalizations or something. But we can really make this work in a large degree, and you might need to tweak what you mean by simplicial object or tweak what you mean by chain complex in some way. But the versions of these, and they're usually pretty fundamental and whenever you have them. Okay. So I guess any questions?
Are you going to write some of the variations?
Sorry, right? What? So the what?
Are you going to write some of the variations now or?
Oh no. Well, okay. So for abelian categories, if you assume that your abelian category emits all limits and co-limits, then you can literally like copy every step. Like nothing special about abelian category or abelian groups appears. Like you can just copy it, and this is fine. So for instance, if you take like category of R modules or something for over a ring, maybe with some niceness on the ring, but
Okay, thank you.
yeah. Okay. So I can talk a little bit about pointed stuff if you want, Crescendo, or we can end here. I mean, we have like 5 minutes, so.
How long will you talk about the pointed stuffs? Like,
I mean, I can. I think I can constrain it to just a couple minutes. I mean, there's not much we need to say.
okay, let's talk about them for a little while then. Yeah.
Okay. Yeah. So I mean, in topological spaces, pointed topological spaces is very fundamental and making a lot of like homotopy theory work. And so likewise for simplicial sets, they become a fairly fundamental thing. And so what are pointed simplicial sets? Well, they're simplicial objects in the category of pointed sets. These simplicial objects in pointed sets. And the main thing I wanted to convey was that like all these constructions that you normally produce in point set topology also hold here. So you can do things. So let's take two pointed simplicial sets. So you can do things like taking a wedge, which is just the union over this point, using this notation I introduced before. You can also take the smash product by taking the product and quotienting out by the wedge, sorry, by the wedge. This is the wedge product, and this is the smash product. And topologically, I mean, this is exactly what you think it is in terms of topology. And so this also lets you do things like suspension. Where we wedge our minimal model of a circle together. And we can use this also to construct higher spheres if we didn't like the first definition I gave before, where we just, sorry, let me write it. So we define this by taking the suspension of the n-1 sphere, and so on. This gives another definition, and I guess it's an exercise to figure out that these are actually the same definition or something. And so the role of these so ordinarily your simplicial sets correspond to things like simplicial homology of topological spaces. And so the role of these pointed simplicial sets is to do reduced simplicial homology. And so we can so I mean if we have how do I say this? So if we have a pointed simplicial set, we can define sort of like these relative chains by taking our normal chains and quotienting it out by our point. Right? So you have our relative chains. And then from this we could define things like reduced simplicial homology by taking the homology of this like the Dold Kan for this. It doesn't really matter if we do something like this. Anyway, there's lots of relationships here, but I mean this is just some slight variation of what we've seen, and is useful if you care about things like reduced homology, I guess.
Yeah.
Anyway.
Also, just so that you note, like he didn't define the loop space, but by taking the functor, the adjunction functor, analogously, you can find the loop space of a loop simplicial set for a simplicial set. So just like in topological spaces we have the loop suspension adjunction, this is one thing we do not have. We do not have the adjunction on in the terms of simplicial set. So that is also something to care about.
Yeah. So this is like a stability thing, right? So
Yes.
if you assume I wrote these inner horns earlier, if you assume that there's like horn lifting, then this is like the same as asking that all your inner horns lift, then you can say that there is an adjunction.
Yeah, so that's the question that you
But
should need.
yeah. So like maybe I'll write
So,
down what the
yeah.
loops are as well. So the pointed loops, I should say, not any loops, but
Also, yeah, you write down. Also, let me mention, just like your topological spaces under smashed products give you a closed monoidal structure, give you a monoidal structure, symmetric monoidal structure, and just like that, your simplicial set also enjoys a internal home functor. The mapping spaces defined similarly, just like the previous one, the simplicial sets one. So, yeah. So these constructions are very analogous. That's all I want to say.
yeah.
That's all. Mm-hmm.
Great.
All right, that's a good point to
Okay.
stop. Let's have a big hand for. Do you want to say something more, Colton?
No, no, that was perfect.
That's great. So let's have a big hand for Colton. Okay.
Yeah, thank
All
you.
right. We can stop the recording now.